Okay. Let's see, this thing, start playing this. Is the stream up? Yeah. All right, guys. Sorry for the delay. And that doesn't work. All right, we're here. Oh, no, it did work. All right, so welcome to Recitation 3. Today, we're going to look at optimization methods and also some other heuristics for training and some best practices that you guys can follow to tune your networks. So basically, we're going to be going through a slide deck, but at the same time, we also want to make sure you guys get some hands-on experience too. So we put together a Jupyter notebook, which is sort of a tutorial and a run-through and has some sample code. And also has some, we're going to pause it at some points and give you all a chance to start implementing some of these optimizers and other initialization methods. So just clone the repository locally, and then run it. You guys can spin up a Jupyter notebook server, and then run the IPython notebook in the Recitation 3 folder from there. So I'll just give 2 minutes for everyone to do that, and then we'll start. Should we keep going? Yeah. Yeah, just check out. The mic. Delete that. All right. It looks like some of you have downloaded it. We're not going to start on it immediately, so we're going to start going through some material. So as we're talking, just try to keep getting that set up, and then we'll get to the notebook. All right. Oh. Okay. This clicker is a little bit delayed. All right. So basically, so far in lecture, we've been talking about the gradient descent algorithm, and so far we've assumed that every update step of our parameters that we take, we make a full batch gradient estimation. So we look over the whole training set, and we are finding the gradient of the error function with respect to all the network parameters. This is a non-convex optimization problem. So basically, in practice, especially when you have very large data sets, it's not really practical to do backpropagation for each update over the whole set of training examples. So most of the time, we want to think about scaling this back. So one may say, well, what if we compute the gradient, the loss, and then compute the gradient of that loss with respect to the parameters for a single example. And many people call that stochastic gradient descent. But the term stochastic gradient descent has been extended further to another thing I'm going to talk about, which is mini-batch gradient descent. So I'll go back to the single example. You can imagine the problem of doing an update step with only a single example. That gradient is a highly biased estimate of the true gradient. So instead, what we do, in order to give us some more computational efficiency, and at the same time also get a pretty good estimate of the gradient, and there's actually a convergence proof out there that says that stochastic gradient descent on mini batches, so where you maybe have 100 examples, where you calculate the gradient and then take a single update step, if you do that over the whole, so basically you partition the training set into batch size mini batches, and then if you take the number of steps to cover the whole training set of mini batches, you actually get basically that averages out to be a good estimate of the true gradient, given that all the batches are IID. Okay. So basically, part of Recitation, we're going to go into how you guys actually can implement this using PyTorch. So one of the standard conventions in PyTorch, and also what makes using mini batches more efficient, is that we take the first dimension of our tensor to be the batch dimension. So this is where your actual data elements are stacked along, and then the actual shape of your data is in the dimensions thereafter. So that also helps with GPUs. So you can send, so say you have a batch of 100 examples, maybe they're images. If they're MNIST images, then they're 28 by 28. And if you're feeding that to an MLP, that becomes 784. So you'll have 100 by 784. And you can send that whole piece of data right to the GPU instead of sending single examples, and you get communication delay, lots of latency. So you actually, if you're only sending example by example to the GPU for computation, you're actually going to get a slowdown just because of the time it takes to load the data into GPU memory. So instead, we actually get a speed up by batching our data, sending that all at one time to the GPU, and running our computation. And yeah, that's that. So let's see. Do we want to switch over to the notebook? So how many people roughly have the notebook up and running? Awesome. Okay, great. So let me go to this thing. Okay. So okay. So basically, here's a little exercise that we're going to do, and we're going to play around with some optimization, tuning, and initialization. So instead of MNIST, I've loaded this other data set called Fashion MNIST, which instead of numerical digits actually has a couple, 10 classes, items of clothing. But other than that, it's exactly the same structure. 28 by 28 pixel images. All the objects are centered, so you don't have to worry about translation. And it's actually the same exact size. There are 50,000 training set members. Zoom in. Okay. Okay. Hopefully that's better on the live stream. And then there are also 10,000 data set members. All right. So here's a sample of the data set. And here is a PyTorch, a network in PyTorch that we're going to use. Very simple MLP. And we're going to use nonlinearities with a softmax output. All right. Rajat, do you want to talk about initialization? Mm-hmm. Yep. All right. So we're going to get back to our vanilla stochastic gradient descent optimizer that we just touched on. And Rajat's going to talk about parameter initialization. So let's play that. Change the mic here. All right.
Thanks. So when training a network, the weights are very important. Like if you think about it, if you have an oracle who just tells you what weights to choose, then it's just done. So that's obviously that's an extreme case, and that's not going to occur in practice. But you can start off with good initializations and position your network in a better beginning point from which it's just potentially easier to get to a good solution. So let's start by some so one way of initializing could be just start off with everything as all zeros, but then everything's all zero, right? So that doesn't make sense. So what if we initialize everything to the same non-zero constant value? So the issue with that is that all of the neurons have the same value. So each of them is exactly the same. So all the updates are also the same. So it's just the same thing all over again. So there's nothing which is breaking the symmetry between the neurons. So that's something that you have to think about when initializing. So one way of initializing could be just random, and hope that you don't have too many neurons with similar weights, so that they're kind of tied together in their updates. So do you want to switch to the notebook, or?
Or do you want to run through the different kinds?
Okay.
Initialization?
Yeah. So that's one kind of initialization. In this recitation, we're also going to touch Xavier initialization, which is sort of like a smarter way of doing this, smarter than random for sure. So the idea behind this is that you want if you consider a single layer, you want the variance of the inputs to be equal to the variance of outputs. And the hope is that, for deriving this, the formula for Xavier, so suppose you sample from a Gaussian and you want the variance of the inputs to be the variance equal to the variance of outputs. So intuitively, the idea is that if you have a small number of inputs to that layer, and you have a large number of outputs from that layer, and you want the variances to be equal. So for the side which has a smaller number of inputs, you are dividing by a smaller number to get the same larger weight as this side, which has more outputs. So that's how you will be able to ensure that both sides have the same variance. And I'm not going into the maths behind this, but during the derivation, this sort of assumes that you're in the linear portion of the activation. So this doesn't work very well with ReLUs because it's not constrained to be in the linear position portion for that. And another thing that we're going to briefly touch upon today, but not explore too much, is pre-training. So it's usually helpful to have. So if you have two data sets which you have reason to believe are similar in some aspects, then you can use the weights that you trained on one of them for as an initialization for training for the other one. And the hope is that when training on a larger data set, which has maybe you have a higher resource data set, you have the pre-training will allow it to pick up the features. And when you use that as the initializations for your specific task, you can sort of think it as in terms of fine-tuning those features to your specific target. So you just have a very good initialization to begin with, and it just
yeah. Usually that's a little bit screwed up if your actual input in terms of format differs, because then the lower level features developed by the network are no longer useful. And a lot of the time, this sort of echoes to how people will take a very fine-tuned network for some task, and if the image, like say image recognition, and now you have a new set of classes, like you've only trained on cats and dogs, but now you want to add like guinea pigs to your classifier, you could actually, under the assumption that you're building up higher level representations through the network, you can then take off the final layer or add another layer, and then basically then put lower learning rates on the upstream parameters, but then have a higher learning rate on basically a fresh new initialized set of parameters at the end, and hope to do better on those new classes. So that's pretty common, and you'll see that.
Yeah, and putting a higher learning rate on the parameters towards the end, that's sort of encourages fine-tuning, because the initial layers have the necessary representations, and you might just want to end up tuning the thing. So
Okay, we're going to switch to the notebook, and we're going to show you guys the actual effects of this. Okay, so right here we have a random initialization, and we have, you describe this.
Yeah, so the random initialization is just in this specific case, we are sampling from a normal distribution, and this is a clean way of initializing by defining a separate function which returns, which sets the initializations. And if you look at line 6, so when you declare a model, you have the option of model.apply initialization. So this recursively goes down to all the submodules of the model, and it accesses this by model.children. So for example, in this, I have chosen only to initialize the linear layers. So you can, depending on what you're trying to initialize and what your model looks like, you can set different conditions and have initialize whatever way you want. And this is another example where I'm just, it's also a random initialization, but I'm using a copy. So in case you want to load some weights from a specific scheme and you have, you can explore this copy version as well. And what we want you guys to try during this recitation is to implement the Xavier initialization. So a hint that I have given to you guys is, so for Xavier, you want, let me just pull up the slides again.
Sure.
Yeah.
Yeah, so we'll.
Xavier. Thanks. So this is the Xavier initialization. For now, you can just assume that gain is 1. And so fan in and fan out are basically the number of connections that are coming into the layer and going out of the layer. So you can try to infer that locally. Oh, how do you?
Okay.
Sorry.
So basically, if you guys want to give that a try.
Yeah. So using m.weight.size, you can infer that locally, and maybe you guys should try to implement that formula using the hint. So
we'll give you guys like 2 minutes, and then we'll type it out, and then we'll run it, and then we'll compare a random init, a uniform init, and then also the Xavier initialization.
for now, you just use it. You can take it to be 1. Like in general, that's an adjustable parameter. So the derivation assumes that we want the same variance, but if it just so happens that you want the variance of this, the output side to be higher, you can set the gain appropriately. But it doesn't matter right now, it's just fun. So.
Do you want to pull up the slide for them? They can look at that.
Yeah.
Do it.
Thanks.
All right. So as you're doing that, Rajat, do you want to run through?
Yeah. So I'm just gonna start. Implementing the thing. So we have to begin with specifying the type of the submodule that we want to initialize the weights for. In this case, it's just linear. So that's the first thing you begin off with. So using m.weight.size, you can get the dimensions of the weight matrix. So the first this element of that is the fan in, and the right. So you can just infer that locally from whatever weight. So think of it in this terms, because this function is going to be applied to all the the submodules, and you have.
I think it's the actual existence. Is it the other way around? Right,
I
matrix
don't-
0.
I don't remember.
But it doesn't change anything. All right, so
Yeah.
I believe that. So keep going. So actually, this should be swapped, fan in and fan out, from 0 and 1. But you'll notice that in the equation, we just sum them together. So obviously, it doesn't produce a explicit bug, but that's not technically correct. So, okay, so now it's corrected.
So this is the formula, and as Ryan said, you're just going to sum them over here, but the correct way is 0 and 1.
Oh, really? It crashed? Okay.
Oh.
Are you sure? Okay.
Okay. So this is the SE that you have a.
If you're just going to add fan in and fan out together anyway, why not just call sum on m.weight.size?
Well, sure, but I want it to be explicitly clear to everyone that you're actually accessing the. It's the same thing. Like, you're right. You can just do that. Yeah.
That's the cleaner way to do it, obviously.
Yeah.
Faster.
But I just wanted to be clear that this is the fan in and this is the fan out. Doesn't matter. You're right. And looking at the previous way of how we initialize how we set the weights, it's the same thing. And
So one of the more subtle PyTorch things here is that, so it's the things that are being so PyTorch represents, one of their abstractions is this thing called a module. And a module is just a piece of a differentiable computation. So a module has like a forward method and a backward method, but obviously because it's an autodiff framework, you only have to specify the forward method, and then naturally, it'll build you up a computational graph, and at the end of the graph, you can then call backward, and then it will calculate the derivatives with respect to the parameters all the way backwards through the graph. So you can see here in this initialization, it's taking in a module and using that same graph that is built up, it's going to recursively call back all the other inside modules, which includes, and one kind of module is linear, which is really just an affine transformation. So it's what you've all seen as a normal MLP layer, but you could also have comp 2D, whatever kind of transformation that you'll see later. So do you want to run it?
yeah, wait. Where's the run thing? Like,
Isn't it below? Dismiss it?
okay. No, but execute this thing.
There it is.
Yeah. Yeah. So we should just. So. Sorry.
We had to run them all.
Uh,
Here, just do it. All right, let's run all this. All right, so we're going to run this now. You guys can run it too. So we just have some code to load our data, and a simple training cradle that will do the training. And then let's turn down the number of epochs so we can do this right now. 10.
Mhm.
All right, let's let this crank. All right, so as that trains, do you want me to just move on to the next bit?
Mhm.
All right. All right, so we talked a little bit about stochastic gradient descent, and as was discussed in the last lecture, we discussed momentum as a way to correct for noisy or steps in your gradient, and this becomes especially important when you're doing stochastic gradient descent. Obviously, we're much more prone to having non-stationary batches. I mean, even though they are IID, you're going to get noise. It's not a perfect representation of the training set entirely. So we want to basically resist sudden changes as we descend through the error space. So the idea is that it's sort of like we basically keep a running average of the gradient, and we use that to update instead of our current gradient term. So you can see here phi is basically what I like to call like a momentum buffer in terms of how we implement it. And we basically let that decay and then also add our current gradient, and then we take an update given that average. So you can see I have this little very inaccurate representation, but you can see how if you have noisy steps, this will smooth out your path. Okay. So also another optimization method discussed in lecture, which is pretty intuitive, is called rprop. So basically, one of the real, assumptions that's pretty poor is having a global learning rate that every parameter should be learning at the same rate. And one of the intuitive one of the problems that I like to sort of think about is the vanishing gradient problem. I think this is a good example of why global learning rates just don't make that much sense. Is that because of the multiplicative nature of the chain rule, your gradients upstream, near your inputs are actually going to be much smaller magnitude than your gradients downstream, near where you're first calculating the error and then back propagating it. So when you first start training, the network is actually learning faster downstream. So imagine you're a baby and you're trying to learn what your grandma looks like, and you're basically learning about the color of her hair without knowing what hair is. The idea is that the later parameters are actually learning off of correlated noise of the inputs, right? Like we're not actually developing a good low-level representation. Like it's not learning what lines are. It's not learning any edge detection. Any of these fundamental, when we make this assumption in neural networks that we're building from lower level representations to higher level representations, and we're combining those to basically optimize directly for our task. But if you're learning, downstream, it really makes no intuitive sense, and you're basically learning off correlated noise until later on those parameters can catch up. So basically, the idea is that we want to have a way to adaptively set our learning rate in an intelligent way. And one good idea is rprop. And rprop only works with full batch. I'm going to get to the reason why it doesn't actually work with mini batches. But the idea is it makes sense. If the sign of your gradient switches all of a sudden, that probably means that you overshot. And what you want to do is we want to shrink the rate that parameter learns at. And if we keep making confident steps in a direction without a sign change, we can actually keep multiplicatively increasing the strength of the learning on that parameter. Okay, so rprop is great, but it fails with mini batches. So you can see that if we make, I think this is 10 updates here, the idea is that so in full batch learning, if this was a full epoch, you would only do a single multiplicative increase at the end. But if this was batch learning, at each step here with SGD, we would be basically the learning rate would sort of explode over the full batch. Even though we would expect there to be a negligible increase over a full epoch of training, if these were our updates. So how can we combine the effectiveness of rprop with the benefits of mini batch training? So that's where rmsprop comes in. Cool thing about rmsprop, it's probably everyone wants to publish any little tiny thing that they find in the deep learning community that gives you like 0.01% error. This is probably the only method it's been only mentioned on a single slide in a single presentation, and that's how it's got its name, but it's very effective. Jeff Hinnon came up with it. And it makes sense. So instead of thinking about sign, we can think of keeping a running average of our gradient, actually the second moment of our gradient, and then we divide our learning rate by this. So if it grows, we want to scale the gradient down. If it shrinks, we can scale the gradient up. So it definitely scales the gradient to reduce the chance of overfitting. So do you want to talk about Atom a little bit?
So the idea about all these optimizers is that given your high-level knowledge about the surface that you're traversing, you wanna be able to make a smart decision about what update to make next. So beginning with momentum, where you're kind of that if you're zigzagging in a valley, you sort of need to start picking up in this direction. So you add momentum, and then you have rmsprop, and which scales it with this. So Atom is like the name is adaptive movement estimation. So rmsprop just shows the exponentially decaying average of the past squared gradients, but Atom adds the average of the gradients themselves. So these two terms are the bias corrected values. So the m hat and the v hat, you just corrected for the bias. And so at the bottom of the page is the update rule that we have for rmsprop. So Atom is pretty much similar, but you just replace it, the past squared gradients with the decaying average of the past gradients themselves.
And sorry, one thing. So in terms of the bias correction term, in machine learning, bias gets thrown around in so many different ways, including what we've been talking about, which is our bias terms in our network. This is different. This is bias correction, meaning so you can see that t is your time step, every update step that you make. So in the beginning, we believe our gradient is highly biased, but over time, as we start averaging, so v is our second moment of the uncentered variance. So as t gets larger, we we're more confident that that's a good average.
So we're going to step back to the notebook for a bit.
Sure. Let's keep that.
Okay.
Oh, yeah, you can also
Yeah.
turn that.
So
We finished training.
yeah, we finished training. We just picked 10 epochs for brevity, and so the normal initialized model was the first one where we were sampling from a normal distribution. The custom one was where we're just doing a random, and this is the Xavier initialized model, and you can see that the test accuracy is just better because Xavier has a better starting point. And we're just going to quickly use the code that we have provided to visualize these. Wait. For some reason, we only have 2 epochs for Xavier, but yeah, I mean, that's probably because we have some stuff saved, but you guys will probably be able to see a nice, using nice plots. And
Yeah, no.
yeah,
That's kind of funny. Do you want to show our photo from yesterday?
yeah, I don't know where it is though.
We made sure that we saved a screenshot. Let's hope there's nothing too embarrassing on my desktop here. Nope, not that one. That's also embarrassing.
The one on GitHub,
Is there the one on GitHub is fine? Yeah. So if you pull up
Yeah.
All right. Got to show off some of my personal gifts I saved. All right.
Yeah, and as a small, concluding the section for initializations, we haven't really talked about using pre-trained weights because that's not the point of today's recitation. But so, for example, if you're talking about image recognition using CNNs, so AlexNet was one of the. So in 2012, they just blew everyone else out of the water. At that point, up till that point, the best error rate on the ImageNet challenge was something like 25% or something like that, and AlexNet just straight away they got it down to 16. Of course, now it's even better, and I think it's better than human performance, whatever that may mean. But the point is, all these models are pre-trained, and the weights are available online, and you can just simply load them and use them as low-level feature extractors and you have reason to believe this works because these have been trained on massive amounts of well-labeled data, which
They're very well regularized.
Yeah.
More data is the best regularizer there is.
Yeah, yeah.
this is the concept of transfer learning, right?
Essentially, yeah.
Well, so I mean, transfer learning is mostly taking some model from across domains.
Yeah.
But this is really we're expecting the same input features, or like similar features, but we're
Yeah.
just expanding our.
Yeah, as opposed to domains, it's just talking about different kinds of data. Yeah, it's related.
But obviously, just like anything you talk about, like artificial intelligence, like everyone will mix up certain. I'm sure someone talks about that as transfer learning, but I'm sure others would object and say it's definitely not.
Okay.
Well, it's also to work with this trial, and let's
Yeah.
just, if we get something with pretty big data trained and fits with high precision, you could understand.
Yeah. It's a good starting point with more data. Yeah. So back to optimization.
Sure.
Yeah.
All right. So basically, just as we spoke about before, we're just going to go over in PyTorch how we can use the PyTorch API, their optimizer API to build simple optimizers. Okay, so here's our vanilla SGD optimizer, just with a global learning rate. I'm gonna run over a couple things I've written about here. You can read about it later if it's still a little bit confusing. But PyTorch, whenever you construct a module or what we've been referring to as a model, it creates obviously it builds a parameter set. So I initialized 3 linear layers earlier, and those generate a weight and a bias for each one. And when I call model, whatever the variable name is, model.parameters, it'll return basically a pointer to all the parameter set. So when in Optimizer takes so you can see here I'm initializing the superclass given the parameters, and these are just the parameters of the network. So all the weights and the biases, and the general idea of an optimizer is that every single time you call step, we're going to take the gradients that were calculated during backpropagation, which are automatically linked inside your computational graph, and we're going to apply them and update our parameters. So basically, one internal data structure is this thing called param groups, and in the group you can set default values here, and these are going to be applied to every single module inside the network. So for example, if we want a global learning rate or some other global hyperparameter, we can just set it here really simply. And something that's really interesting too, there you can actually customize. There's another optional parameter thing I can add here, like options. And options will let me actually set different parameters for different modules. So if I want different learning rates, so if I'm going to stack on a new layer to a network, I can set a small learning rate for the earlier layers and something bigger later on. So basically, I'm going to loop through. So in the group 2, it also contains a hash to all the parameters. So I can simply pick up each parameter, which is like the weight bias pair. I can take the data here from it, because right now it's a more complex structure. It has other features. And I can, so one important thing here that you're not going to do a lot in PyTorch, but you'll do in some places like optimizers, is you're going to do in-place operations. And this is important because it's much more efficient. You're not going to create a new copy of the data. So simply here, we're going to take the data and we're just going to add the gradient that we calculated during backpropagation, and just take the negative of the learning rate. Yep, that's pretty simple. And we can extend this to momentum. And in this, we're now going to use something called self.state. And obviously, self.state is a stateful data representation inside the optimizer. And what's interesting is that your parameters are actually uniquely hashable. So, momentum here, this is just another hyperparameter. Like learning rate, we're applying it globally. This is your beta that you've seen in other slides. But now we're actually going to create the momentum buffer, which we're going to preserve throughout the optimization process. So we basically when we start training in this optimizer, you're going to create the buffer here inside here as just something that's the same size as the gradient, and then if we've already created it, we're just going to keep loading the buffer, and then we're going to do the first term in our momentum equation here. And then we're going to, and then we do an update to our data. This is the second line. Okay, so right now, it's your turn. So here is the atom optimization algorithm pulled right from the paper. And here is a empty atom optimizer. And you guys should go ahead right now and try implementing atom using these same constructs here. So just give you guys 5 minutes, and we can come around if you guys have any questions. People on the live stream should message us on Piazza or post on the live stream chat, and then we'll come back in 5 minutes and we'll write it up. Zoom in. guys, show of hands. Who wants to keep working? Who wants to see us start writing it? You guys? Okay. Start writing it. Yeah, that vote wasn't very clear. Which option you were voting for? Who wants to keep working for a little bit more time? Who wants us to start running through it? All right, we'll start running through it. Okay. Yep. So as we did before, we're going to loop through our parameters. Just going to set a little constant here. So in case we have round off error for our divisors, we can make sure we avoid div by zero errors. Let's set our hyperparameters. Sorry, I misspoke. I was looping through our parameter groups, which also associate themselves with sets of parameters. But now here we're actually going to directly loop through our parameter data. We're going to take our gradients. So we're going to get the current state of our parameter set. Oh no, our parameter here. Okay, just a quick recap here. We're creating a buffer now for our first moment and second moment running averages. And also, we just want to keep track of what update step that we're on. So that way we can set our bias corrector correctly. So if we're on step, for any step after the first step, we're just going to load those from the buffer, or load the buffers. Oh yeah. Forgot to load our time step. All right. So for an in-place operation, I forgot to mention, they're basically most standard arithmetic operations. Normally, if they're not in place, they just don't have an underscore, but you can make them underscore in place by adding underscore after them. So we're just going to increment our counter, step counter. Now we're going to implement the meat of the algorithm. So these two lines are our first biased estimate updates. Yeah. Oh, yeah. I forgot to write that. This is here.
No, in the second.
Yeah, it's only the second one. Yeah. Thanks. Thanks for catching that. And then our update. Oh yeah. In place. Shouldn't matter either way. Yep. All right. So that's it. It's a little drawn out to do this, but it should give us an improvement. So just look up when you guys are done implementing it, and then I'll move on. Sure this thing. All right. Let's continue. All right, so let's run these. Do you want for 10? Yeah. Okay, then we'll let these things cook and then we'll come back to them. Here's a preview of the results from the last time I ran it. You can see that we basically, the longer you run it for and the more complex your error surface, so probably the more primers you have, you're going to get greater improvements from using these. Yeah. And then when we visualize them, you can just see how with Atom, your rate of convergence is much greater. Okay. So what am I going to talk about now? Do you want to talk about this?
Okay, so while we're waiting for the networks to train using our optimizers, yeah, so another important thing about when training networks is tracking metrics. So there are many hyperparameters to the network. You can set different things and different learning rates, different sizes, everything. So you need a consistent way of comparing all of these across different architectures. Because you want to figure out which is the most appropriate for your task. So which is why it's important to track metrics. So for example, like you could track the loss per epoch. That's something that you're already doing anyway, so that's easy to do. Or you could look at the training error, which is expensive, but it's okay.
I can speak on that. So
yeah.
one of the sorry to interrupt. One of the things about training error is a lot of the time And when people first start out, they'll think, oh man, after every single epoch, I got to run through my whole training set and then test it. And that's pretty slow to. But one thing that you can do, which is an estimate of the true training error, is as you train, you're going to do a feed forward before backpropagation. Take your estimates, calculate their predictions, and then have a running sum of of the model's correct predictions on the data, and then at the end of each epoch, just take that running sum, divide by the total samples in the epoch, and then you get a pretty good estimate of your training error. That's how actually I calculate a training error on all of these curves. So that's a good little tip to keep track of that.
Yeah, and it's easiest to see what's happening with visualization, so it's strongly recommended that you figure out how to use matplotlib or Wisdom or something, and for tracking your metrics. Do you have a question?
Is there any one use the gradient norm to track the metrics?
Yeah, you can track the gradient norm. Wait, are you asking for a reason for it?
Will it be helpful?
Sorry?
Will it be helpful to tracking the gradient?
The magnitude of the gradients?
Yeah.
I'm trying to think of how that would help you. I mean, I think tracking the magnitude of the gradients per parameter in the network, or like the mean across a layer or something, I think that could be helpful to tell you the relative speed of learning across, like different points in your network. So,
Yeah. So for the people on the stream, the question was whether it could be useful to track the gradients as part of this, and if you look at the gradients per parameter, and that might be useful to compare the relative learning rate. And yeah, so one of my favorite methods is early stopping. So far the premise was that you have a data set, you track these values, you run over all your data, and see how it goes. But you can also keep doing this as you go, which is which is the online way. So let's go back to this this slide. So if you look at this is not a good example, but there are some. If you notice that your network is slowly converging, and then the difference is sort of becoming insignificant in the large scheme, so you can sort of stop at that point, and I mean, there are some theoretical.
as your validation error.
Yeah.
Right.
Yeah.
So basically, neural networks are fantastic at being, as representational machines. But part of the problem too is they also are they suffer from high variance, meaning that if you fully train them out and you give them different training sets, you're going to get sometimes very different representations. They're really good at basically what I'm saying is they're really good at overfitting. So the reason that we keep track of is a held out validation set and training in your normal training data. So that way, every single update step or epoch, you should be checking your validation accuracy on that small set. And even if you're doing better on training data, if you start performing worse on the validation data, early stopping is just a way to say, all right, we're going to stop training now because we've done as good as we're going to do on our validation data. It means probably that we're going to generalize better than if we keep going to convergence on the error of our training set.
But this also raises a lot of practical considerations, like what would be a good time to say that, we should stop. Should you skip the first few epochs because you know for sure that it's just not a good idea to stop there, or how many epochs to wait before you conclude that there's no further progress being made, how quickly you make these assessments. So all of these add more hyperparameters. So it's up to you to find whatever works best for you, but it's a good idea to have early stopping in general. So one more topic that we want to touch upon today is cross-validation. So in most real-world, in some real-world data sets, you might not have a separate way of testing the performance on unseen data because it's just unseen. So instead of having, in cases where you don't have unseen data, you can sort of emulate the existence by partitioning your data set into a train set and a validation set. So one could do it into k divisions and train on k-1 and validate the results on the kth, and you could do that across all folds and average, but it's just usually it's sufficient to have just an 80-20 split and train on 80 and use the 20% of the data for validation.
If you have 20 to spare, right?
Yeah.
If your data set, if you believe your data set is small enough, too small for the network that you're trying to train, if you took away that 20% of the data as validation, then you can use k-fold cross-validation to emulate that split, but then keep swapping the subset that you take out across the training set.
Yeah, so if you have k-folds, you pick one of them as a validation and keep doing that for all of them.
So what's cool is that you do train across all the data,
Yeah.
but you're still able to.
But your model encounters all the data during training, but during each instance of, during each fold, it is not viewing the held out data so you can sort of say that it's a held out data which hasn't been seen and can be used for validation. So if you look at the training, in the examples that we have right now, we just run it for 10 epochs or 20 epochs. You can try that for more. So what usually ends up happening is if you keep on training for a really long period of time, your training error will go down because you are explicitly making updates so that it keeps going down. But then there's this inherent trade-off between the bias and the variance. So if you keep doing that, you're not able, you're overfitting on the test data. You're able to recognize all of the test data really well, but that does not extend to unseen data. So that's just not what you want to do. So if you have a training error and a cross-validation error curves, so right at the point where it sort of, the cross-validation error starts going back up, that's kind of the region where you can conclude that generalization is not able to generalize well after that if you keep training after that point. So in idealized curves, that's easy to recognize, but you might have something like this. So you don't know where exactly the point lies where you can say that, okay, this is the point where maybe we should stop. So, and this is important because we want to prevent overfitting, obviously. And additionally, if we have concepts like early stopping, you can just stop before it you can save time by stopping beyond and not going beyond the point where it's not converging. So another topic that we want to touch upon today is hyperparameter tuning. So we have a lot of parameters, and so in the current recitation, we just set things to some values, but you might want to tune them and see what performs best for your data. But so in general, so let's say you have 5 different parameters, learning rate, and stuff like that. So it's sort of like a combinatorial problem because you want to be able to check all possible combinations, but that's just not practical. And so one way of doing it is grid search, where you define a range of values for each parameter and just imagine it as a grid in that n space and go over each combination. The good thing about this is that all of them are independent, so you can parallelize this and see whichever works best. But the bad thing is that you are manually defining your own space. So if you look at the example in the slides, on the left we have a uniform grid, which is what you're probably going to be defining, which does just not sample the true distribution very well. But instead, if you have a random initialization, you could end up having more points on the peak, and that might end up working better. Also, why we need to do this is that it's not the case that you can optimize for one parameter and fix it, because all of these interact with each other. So if all of them were independent, then you could just iterate through each of them and just that would be much faster. But you have to go through all the combinations. So another way of, let me see if I can play this. So another way of doing that is Bayesian hyperparameter tuning. So you sort of assume that your hyperparameter space, you assume a smooth function that maps the hyperparameter space to some objective that you define. And so in this example, it's on the x-axis is a sigma. So this simulation, this specific simulation that Max did is transforming the hyperparameter space to a single cost using an SVM with an RBF kernel. So that's the SVM parameter. And the darker values are better for the model. So basically, given each coordinate in the hyperparameter space, you evaluate where you are with respect to the cost. And based on that, you predict your next update. So that's just a more informed way of exploring the hyperparameter space, but you can explore that. And do you want to, yeah.
All right, talk a bit about regularization. I mean, so this sort of comes back to the problem of overfitting. A general and the bias variance trade-off. In general, in machine learning, we think about Occam's razor. Models that should be made, to explain something should be as simple as possible. So, I mean, one of the classic examples is you draw, a graph with 4 points on it, and you say, what function, and they look a little bit linear, they could be exponential, and you really don't know, and you're given these data points, and you're trying to fit a function. So the question really becomes, what is your, I can draw squiggly lines up and down through those points. I can draw a straight line. I mean, many of us intuitively would say, well, we should just fit a straight line, and that goes to our intuitive sense that we should pick the simplest model that explains the data. So in neural networks especially, because they have such high representational power, and actually there is some implicit bias in the way that in their representation, due to the linearity of their of the center regions of the activations, you'll actually see that if you give them a whole bunch of points and you show them to separate, you'll actually get smooth curves. You actually may get better representations with sharp edges that try to cut around the data, but actually neural networks are restricted to smooth curves. But other than that, they can, they suffer from on the training data. So there are some ways that we can actually penalize the network in the objective function. So let's talk about those. So L1 and L2 regularization. So this is just saying that larger weights. So let's actually talk about L2 first. This is the most common. So we penalize larger weights, motivate smaller weights, simpler representations, and we don't overweight. So an intuitive way to think about it is if you have some large weights, that makes the network very sensitive to specific inputs, and that's kind of a sign of overfitting. If for a certain example, there's some feature that's like a tell-all that's really good at predicting that specific data example, but it's not a good general rule for the data that you expect to see. And sort of the math behind it is that if you can imagine the x squared when you square the parameter, that parameters that deviate, that are extremely large, get penalized, but as they move towards zero, if you draw a line and then you compare that to the to x squared, you see that close to zero, actually x squared is smaller than a line. There's a point. So you're not necessarily trying to shove the weights to zero, but you're trying to keep them small. Whereas with L1 regularization, where you're just taking the absolute value, this is penalizing non-zero parameters. So the gradient is really just -1. It's just trying to shove it back down to 0, and this will motivate sparse representations, which in general you can think about in some cases are, I mean, it is a simpler representation. It's more explainable. Okay. So another form of regularization that was developed by Jeff Hinton is called random dropout, and there are a couple actually ways to think about this beyond regularization too. So the idea is that you can imagine one topic in machine learning is ensemble learning. So you basically build a bunch of models that have that maybe had a different initialization or have converged to different local minima. And if you average these predictions, you'll generally do better. So dropout, what dropout does is we take each connection in the network, and as we train, we randomly drop the connection. So we're basically averaging exponentially many different topologies. So beyond just regularization, and also it motivates basically the model itself can't learn, like, it has to learn a very distributed representation, right? Because if it can't rely on a single, maybe network circuit here to do some kind, like, that computation has to be scaled across, and that's not necessarily, and there is actually in the paper, you can read further, there's a real argument why that, I mean, you would say it's definitely a disadvantage for the network to have to learn each different part of the representation in a distributed way. That seems like something that's suboptimal, but there are arguments proved by the empirical effectiveness of dropout as to why the network doesn't necessarily follow just copying the representation, but actually learn something that's it learns a more distributed. Sorry, what am I saying? It doesn't just copy the pattern recognition through the whole network. That way, if it gets dropped out, it still works. It will just learn a more robust representation. I can post something about that later. Yeah, and as I said, it's also, there are many ways to think about it. People actually don't exactly entirely, lots of arguments as to why dropout is so effective. It is also somewhat equivalent to paying a sparsity penalty. The more sparse your representation, obviously, so if you're only relying on certain neurons to do most of the heavy lifting, then you're screwed when they get dropped out, and you'll perform poorly. So the network has to adapt to that. Okay. Do you want to talk about batch norm?
Do we have batch norm?
We do, but no, it's the solve version, so it's not there. Okay. So batch normalization was a serious improvement. How much time do we have? Oh, we're kind of out. I'll spend 2 minutes on this. It's very simple but extremely effective. The idea is that there's this problem with internal covariate shift. So normally we assume over our training data that our covariates. Usually we'll normalize our input data such that over the training set, it's like even if we do mini batches, it's stationary. It's the same mean and standard deviation. But if we actually think of our network, each layer as its own set of features or covariates, as we learn and as the parameters are changing, each layer has to account for a shifting distribution of its previous inputs. And so for the example, from the problem that I brought up earlier of vanishing gradients, where you have layers that are learning at different rates. So as maybe the lower level representations actually start learning better now, while all those higher level the neurons farther downstream now have to adapt for the shift. So one of the ideas is, well, what if we just normalize the activity at each layer? Well, that presents a problem because now that you've normalized, you are now across each batch, you are now restricting the representational ability of that layer, right? You're now shoving the values So one of the ideas is, how about you adaptively do this? So you actually add a element-wise parameter to each of the layers now. So that means each unit or neuron has a specific parameter that allows, or two parameters, one to scale and one to shift. So you normalize, and then the network is now allowed during training to rescale and shift. And you actually add these to the computational graph. And you can see these two parameters, gamma and beta. These you can see multiply, scale, and then reshift to allow you to get back to the previous representational ability that you had before for each unit. And this is like super effective. It really speeds up training and convergence.
We want to go back to the notebook. Did we complete
No,
that?
we didn't. There's nothing in the
Okay,
notebook.
cool.
All right, guys. Sorry to keep you late. Thank you very much.
Recitation
And then-
such.
Sorry.
So the recitation
Yeah.
is at the same time as last, at the same place.
TA hours.
I'm sorry, the TARs are at the same time as and location as last week in an SH atrium.
It is the graph. Oh, it is. Okay, we can repost it. I think it was just because I exported the PDF really quickly, so I can export it on higher quality. Yeah, and if anything we said today was unclear, which there was a lot of unclear stuff, please just come to TA hours and we can sort it out.